It's actually quite an honour to be here, highly unexpected, and therefore it does require some acknowledgements. I have to say thank you to Ravi, and thank you to IRT, thank you to Monash for providing me with another chance to express myself on one of my favourite subjects, mainly the wheel-rail interface. So that's the topic of my discussion. Wheel-rail interface. I've been enamoured by this little contact patch that you see up there for a large number of centuries. The talk that I will be giving, I'll be talking about some of the basic principles. This is where the high-tech stuff comes in, okay? The general influence of this wheel-rail interface and this little nice contact patch. Some of the specific consequences, that just allows me to show some nice slides, okay, some nice looking slides. I need to talk about, I know that you shouldn't really dwell in the past, but there are two case studies that I'd like to discuss. Obviously the BHP Iron Ore, Mount Newman Mining, BHP Billiton, whatever their name is, early days, for the first 20 years or so. Another case, the interesting case study is the interstate lines. That's an interesting one, particularly interesting one. The improvements that we have achieved and the potential future activities. So in a nutshell, that should take 10 minutes, and then we can have a long discussion. This is the tech stuff. This is the high-tech stuff. If you work in this field of wheel-rail interface, you're really in if you know just about 4 or 5 terms, okay? And then that classifies you as an expert. And people tend to pay you a lot of money for talking about connecity, for example. Well, the connecity that people talk about is really the angle. Oh, I did the wrong thing there, obviously. The word connecity is the angle that the wheel taper, the wheel tread. Here is your wheel sitting on top of a rail, wonderfully so. They're brand new wheel, brand new rail, and it's the angle that wheel tread makes with the horizontal line of the axle. Connecity, that's a wonderful, flows off the tongue. And of course, if you have a cylindrical wheel, the connecity is 0. If you have a 1 in 20 wheel, conical tread, the connecity is 1 in 20 or 0.05. That's the connecity. That's not good enough really, because it only applies to one rail. Generally, most systems actually go on 2 rails. In most cases, there are some cases where 1 rail is sufficient, maybe. So we now talk about the next step is this is the upgraded, okay? You passed the test on connecity, and now you're in your postgrad work. And now you come across the word effective connecity. This is the real stuff, because as you have a wheel set, generally a wheel set will move from one side to the other, and you can see that the effective connecity is the actual angle that the wheel tread makes against the point of contact on the rail. And this is not necessarily at the centre line of the rail. It's usually for one rail, it's usually around the gauge corner if you're in curved track, and for the other rail is somewhere in there. And there is a simple equation that can be applied to calculate effective connecity. You have this delta R, which is the rolling radius differential. This is the third term, okay? You're in your masters at the moment. We'll talk about rolling radius differential next slide. And you have this value Y, which is the difference in distance between the track center line and the wheel set center line. Now, one would think that usually that distance is 0. It never is. Okay, so that is why that value is there. So, effective connecity. You'll understand why I'm mentioning all of these things, because I will be talking about them a little bit later on. And now you have the third, a rolling radius differential. Obviously, that entails a delta for the differential. And the rolling radius differential is the difference between one radius at the contact point in terms of the wheel less the other radius on the other rail at the contact point. Now, when you have a wheel set, a lovely new wheel set, and you have brand new rail, and you manage to get that wheel set right at the center line of the track, so your track center line is the same as the wheel set center line, obviously the rolling radius differential is 0. There's your equilibrium point. The wheel sets love equilibrium. So do I, actually, but sometimes you can't get it. So that's the rolling radius differential. Now, again, in reality, what happens in track is that the wheel set moves towards one side of the rail, of the track, or the other side. And as soon as that movement occurs, then one radius becomes different to the other. And if this radius on this left rail is greater than the radius on this rail, the rolling radius differential is positive, and the wheel set then wants to go back to an equilibrium position because it doesn't like being in a non-equilibrium position. And that gives you wheel set steering. And that's essentially a very nice thing to have if you can control it. Wheel set steering in railways is essentially similar, soft tyres on the left-hand side and hard tyres on the right-hand side, and that's essentially what they're trying to do. They're trying to establish a rolling radius differential so that they can get steering, good steering, to go around those curves without going up the backside of the car in front of them. So they've learned from the railways, you see. Great. Okay, so that's the rolling radius differential. And of course, if you want to get the highest rolling radius differential, which will give you the highest steering force, this is the kind of condition you would like to get. With contact between the wheel throat and the gauge corner of the rail, just at that point, that is quite a large radius, and towards the center of this rail, it's a relatively small radius, so that gives you a pretty high rolling radius differential, and hence high steering forces. Now, high steering forces you require in curve track so that you don't wear the hell out of the rail that is on the outside of the curve. So that's it. That's 2 out of whatever. Now, in real life, of course, it's all set up. Nothing really matters and makes sense because you've got worn wheels, you've got worn rails, you've got rails in curve track, you've got rails in tangent track, and you can see that you've got all kinds of contact points occurring, so you've got a whole spectrum of rolling radius differentials and effective conicities. However, of course, people that are involved in the industry will say that that's fine. We can analyze that, no problem at all. Okay. So the aim of wheel and rail profiling, for example, is the ability really to control the rolling radius differential and effective conicity, and hence the wheel set steering characteristics and the dynamics of wheel sets as they travel down the track. So instead of having this fellow totally and utterly upset, you have these lovely smiley faces. Okay. So what are the requirements? When you start looking at the requirements of wheel and rail profiles in the contact patch, you have different requirements. You have the tighter curves. I didn't actually appreciate what time I started talking. That's fine. Okay. You have the tighter curves. And the tighter curves, by tighter curves I mean something that is up to 900 meter radius. So you have 900 meter radius down to 200 meter or less. In the high rails in these curves are the outside rails, the ones that wear out faster. Here, of course, the main aim is to reduce the flanging forces applied by the wheel sets, and also the contact stresses between the wheel and rail, because contact stresses will affect the defects that you get. So the high rails requires a high rolling radius differential to get the good steering towards the other rail. So that reduces the loads, lateral loads, and reduces wear. The contacts also have to be relatively conformal to each other rather than point, to reduce the contact stresses, and that sort of reduces the defects that I will be showing to you a little bit later on. So on the left-hand side, obviously this is a no-no, because you got almost point contact here. Very, very good steering, that one. Very low wear, that one. But that will produce defects very, very quickly. And this is essentially what you would like to do. You see, nice conformal, and that receives the green tick of approval. On the low rail, the situation is that you really, in the tight curves, the low rails very, very quickly, they require central contact, which is also conformal, because if the contact is too narrow, then the material will start forming corrugations, will start forming rolling fatigue defects, and so on and so forth. So that's essentially what you like. You don't like these kinds of things occurring. Once again, very small contact, and therefore high stresses. And when you get these kind of hollow wheels, they're called, and making contact like that, that's a no-no as well. So the one on your right is what is required. On tangent track or shallow curve, tangent track is straight track, and shallow curves down to approximately 9 or above 900 meters. The requirements are in direct conflict with what you require in curve track. Now, because in tangent track, your primary aim is to keep the axle stable, the vehicle stable, so it doesn't oscillates from side to side. And if you get those oscillations, nasty things can happen, as I will mention a little bit later on. So what you need to do is to have a low effective conicity now, less than 0.15 here. And you also, of course, because of that equation that everyone remembers, that is equivalent to a low rolling radius differential. So the best way of getting these parameters is to keep the contact nice and central. Here it is. This is what happens when you pass 10,000 wheels on a piece of rail in a straight track. The contact should be right in the middle there. There shouldn't be any contact on either the one side or the other. That's pretty good. So that's what you require in straight track. Now, therefore, you've got conflicting requirements. What you do, you can't fiddle around with the wheel profiles. They become worn and so on, and they go all over the system. So what you do is actually be smart, and you control the rail profiles. So you put different rail profiles in curve track to tangent track and shallow curves. So you ground the rails with different profiles, but you also use grinding, of course, to remove defects, and if you've got surface defects and so on. So grinding serves two major purposes. It controls the rail surface, and it cleans up the rail surface, and it also puts in the rail profiles that you like to match with all the wheel profiles that are running around the system. Okay, wheel rail contact stresses. This is another one. Now I take great pride in saying that I've spent almost sort of 44 years examining and trying to control something that is about 5 to 6 millimeter wide, about 10 to 12 millimeter long, and it's got a active depth of about 6 millimeters or 8 millimeters. So you've got this little contact patch here that every wheel makes. The thing about it, of course, is that that's one wheel. Now there are probably 100,000 to go, and that's in a week. So each wheel forms a little patch, and it's individual to that wheel. And so the loads, the effects build up, and you've got the vertical loads that are applied, and you've got the lateral loads that are applied. These are the sort of normal things, nothing very exciting about those. But at the wheel rail interface, you actually have creep forces. Someone has envisaged this word creep, and you have longitudinal creep forces, lateral creep forces, and they are due to the sliding of one surface on another. They have got nothing at all to do, very little to do with a vertical, lateral, whatever it is. As long as you have sliding surfaces, you're going to have these creep forces. Now, creep forces are essentially associated with the development of all kinds of surface defects in rails. They are responsible for all the defects. You've got low creep forces, you will have no defects. You have high creep forces, you have defects in both wheels and rails. So they're very, very important. And just to give you a bit of an idea, are affected. The creep forces are affected by the vertical wheel load by a certain amount, the radii of the wheel against the rail by a certain amount. But the greatest effect that affects creep forces is the traction forces that you apply. The creep stresses is the traction that you apply on the system. And if you have wheels that are freewheeling, loading and so on, and no major effort and so on, this is the only graph that I will show, by the way. I'm sorry about this. No, actually, there are two. This is the first one, much more complex than the second one. This graph plots the stress in the rail as a function of the depth below the wheel rail contact. I mentioned in the previous slide that when you get wheel and rail contact, the stress actually penetrates the rail and penetrates the wheel to a depth of 6, 8, or even 10 millimeters. So here is the stress, and here is the depth. And you can see that under freewheeling with no traction, you get a maximum stress, shear stress, about 4 or 5 millimeters below the contact zone, below the rail surface. And so one would expect that defects will initiate below the rail surface where this maximum stress occurs. If you put any traction at all on the system, you can see the change that occurs. You're not only increasing this maximum here, but this value here at the surface goes way, way, way up high. And so that the more traction you put on the system, the higher is the stress near the surface of the rail and wheel. Now, this is just on a sideway move. You can anyone can sell high tractive effort locomotives, can't you? If you've got all these high traction locos, less money or whatever it is. High tractive effort, high traction. So no one among the locomotive manufacturers actually mentions the destruction that each high tractive effort locomotive does to the track, to the rails and wheels, and the track, of course, and so on. But, I can save you a couple of $1 million because you're not going to require so many locomotives. Oh, yeah. So one of the ways, of course, of getting traction is to either go to steeper grades or buy high tractive effort locomotives. Good fun. Right. What are we on? Yes, Johnson has to come in. A shakedown limit is a wonderful diagram that Johnson came up with, and he said essentially that once again, he said that you've got your traction coefficient here. This is a ratio between the applied load and the shear stress of a material. So obviously the higher the shear stress, the higher the strength of the material, and so on and so on, you get to lower values. And he said that under a wheel rail contact, you have 3 zones that exist. One is an elastic zone. Here, nothing happens. The materials are elastic. What a waste of time. No challenge. Nothing will happen. So you're not really squeezing the material to its capacity. You're playing it safe. On the other side here, you have a repeated plastic flow, and it's called ratcheting and what else? I don't know. So quite a lot of things like, the material is just oozing out. The material behaves like chewing gum, and it mushrooms and forms corrugations and so on and so forth. Obviously, that is a no-no region because the material won't stop. It'll keep on going like that. Doesn't matter what you do to it, it'll keep on going if you're in this regime. Now, this region here is the beautiful one. This is the challenge, because what happens in that region here, called the elastic shakedown, is that you actually do work harden the material a little bit, and so you are squeezing it, but you're controlling that work hardening process So you're making the material better, but you're not destroying the material. So the objective is really to be in this zone here. For materials guys, this essentially means that in this zone there, the material work hardens. And if you are nice to the material, you baby the material and so on and so forth, you will see that by doing that, you can get, this is a normal rail, a standard rail, under 30-ton axle loads. It started off at a hardness of about 270. This is the base hardness. And you can see that over time, that hardness actually increased. And it actually, and that work hardened zone is about 8 to 10 millimeters deep. So there's your precious material. That's worth a heck of a lot of money, if you can control that. And that, of course, is a perfect case of control that came from BHP, a Mount Newman mining company, before they turned into a BHP conglomerate kind of thing. And so that's what you get for control. Now, once you get a situation like that, you have an excellent performance. You can get excellent performance. This is where you also have very exciting time in saying, okay, how do I get that? I need plastic deformation. So how do I get plastic deformation? I need to overload the material. I have to apply a high load, because at low load, I'm not going to get any plastic deformation, so I'm not really squeezing the material dry. So I have to increase the load, and people start getting very, very testy about that, nervous about that. I also require a material that is soft, because if I have a harder material, in combination with a low load, it's not going to work harden at all. It'll be in the elastic regime. So the best thing to do is to actually, well, you play, okay. I'm doing the extreme situation. So in a jokingly sort of fashion, Malcolm Kerr and I used to, who's the chief engineer at Railcorp, used to say that when you lay a track in a passenger system, low loads, so the material doesn't work harden too much. What you should do is actually bring over a heavy-duty iron ore train with 40-ton axle loads, run that over the system, the material will work hard, and then piss off the work train again and run your passenger trains over it. So we used to say that. Unfortunately, we used to say that to the general managers and so on. So they actually believed it. So anyway, we had fun. What happens at the interface layer as well, you have to think about it. It's not only the wheel and rail, but you also are introducing a third body in there most of the time, either on purpose or not so much on purpose. You have lubrication that is introduced in many instances in curved track to reduce the wear. You have friction modification that is introduced to reduce the noise and control the actual traction of the wheel-rail interface. You also have iron oxides. The rail will rust, of course, and it turns into an oxide. You have leaves and dust and so on and so forth. Adelaide has its centipedes or caterpillars or whatever it is. That's essentially what they always bloody say. It's a bad month of the year kind of thing. We have caterpillars going from one side of the track to the other, and therefore we're going to get wheel slip occurring. I mean, obviously. You don't run trains when the caterpillars are on the move. And you've got brake shoe debris, sand, you've got dust and so on and so forth. The actual friction at the wheel-rail interface can change from about 0.1 when you have wonderfully lubricated conditions to 0.6 when you're running dry. Obviously you don't want to run 0.1 on the running surface of the rail where you're trying to get a little bit of traction, because otherwise that train is not going to go uphill. And there are many, many, many instances. I mean, you just go around. If you like listening to the clickety-clack in continuously welded rail, where the clickety-clack shouldn't be there, you run on the Victoria system and you hear all the wheel flats going around, where the wheels, sort of round wheels, well, some of them are not so round, maybe rhombohedral or whatever, run over rails that have wheel bones. But I'll show you in a... But there's more to come. Okay, what's the effect of the general effect of the wheel rail contact? A lot. This is essentially what wheel rail does to the system. It affects the plastic flow of the rails. If a rail then mushrooms, you will see later, then the gauge that you actually set the track at has no meaning, because all of a sudden your track has tight gauge. Now it also affects the corrugations. If you get corrugations, nice corrugations, of course, the track starts to vibrate and the ballast starts to flow. And you generally don't try to go on a train that goes after that, because you generally have, you hope that you're not going to have 40-degree day, centigrade day, because the track will buckle. You lose track stability. You got your traction defects, you got wear limits, you got wear, you got rolling contact fatigue defects, and obviously they influence the way you test the rail non-destructively. You got noise and vibration coming through, and the last one on this side is signaling. That is a very interesting one that someone else that will be talking about signaling will mention if they've got any guts. Okay, how the wheel rail interface actually affects signaling. If you don't have any gut, if there's no one talking about signaling, you just look at the track that's been closed on going from Melbourne, from Traralgon to the coast. Shouldn't be saying that. I mad to myself that I'm not going to say anything about that. Signaling. Okay, here we talk about some of the consequences. Wear. Wear is not too bad, because usually wear occurs over a number of years, and you can monitor it and you know when the track is going to collapse on you. You know, preferably when the government is changeover or where your chief engineer is pissed off and a new one comes on, you arrange the wear rate to correspond to the new engineer and not in your lifetime. So he's going to have the hassle of getting new rails. And that actually occurs particularly on the gauge face of the high rails in the tight curves. And of course, if you start getting into a nice heavy-duty wear regime, you get this wonderful wear debris that falls out. You can see all these shiny bits. Fantastic, really fantastic. That means that you're in the proverbial poo. The rails are not going to last very long. On the positive side, it depends on which side of the fence you're looking at. If you're a track guy, think about it. Only 20% of that belongs to the rail in passenger situations. 80% actually belongs to the wheels. So if you're a track guy, who gives the stuff? You know, the problem is the mechanical guys really give us stuff. So most of that debris, it comes from the wheel, simply because the wheels in passenger traffic are soft, and so on. We won't go into high-tech stuff here. So you try to avoid that, and you can avoid it in a number of ways, and we know how to do that. Corrugations. Okay, we got these are the corrugations that we talk about. You got short pitch in some systems, 30 to 50, 90 millimeters in wavelength. Usually they occur in passenger traffic in curved track. And these are the big buggers. These are the long pitch corrugations, 150 to 450 in wavelength, and they can grow to be very, very deep indeed. And all you have to do is to have a look at some of ARTC, Melbourne to Sydney system, to see the kind of corrugations that theoretically you can get. We didn't actually knew that you could grow them that much, but obviously you can under certain conditions. Defects. You've got a range of defects. So you've got the wonderful things called rolling these are a whole family of defects. Rolling contact fatigue defects, RCFs, gauge corner cracking, running surface cracking. You've got great big pieces of steel falling off. Fantastic. That's really good safety. Usually you don't get a derailment there, but you keep your fingers crossed. And some of these actually grow into transverse defects. And the problem with these, of course, is sometimes if you don't detect them, they will grow through the rail and you get a rail break. And every 10 or 15 rail breaks, you get a derailment. You know, so what? As long as no one is riding on the train at that time. And these became a very hot potato, these kind of things, because some of you may or may not have heard about Hatfield, the disaster that they had in England, some sort of 20 years, I don't know, when, 20, 15? I don't know, time just goes by. And there, of course, the thing that happened there is that they killed off, you know, half a dozen or so, and then they spent millions and millions of dollars trying to solve a problem that everyone, well, some of us knew existed anyway. These are also rolling contact fatigue defects, and sometimes they look pretty nasty, like the squats on the left-hand side. These are squats that actually develop from those fine cracking, and you can see these cracking in the wheels. You can see millions and millions and millions of these cracks occurring in wheels as well. So they occur in both rails and wheels. You have what are called thermal traction defects. The previous slides, the rolling contact fatigue, are pure mechanical in nature. Stress, overstress. These require both traction and heat. And here you have the typical wheel burns that I was mentioning before. It's just a piece of steel that falls off and creates a bit of noise. Unfortunately, sometimes it also breaks the rail. That's all right, that's fine. And on this other side, you have what are called squats. They only occur on one rail, but they are sort of similar to those. And you can see that they're pretty good chunks can fall out. That's okay. And these are more of those. You can see this little line. A wheel has skidded there. That's a skid. And those squatty defects have started to initiate from that skid. And here's a wheel flat that you get from a wheel. Plenty of those. I mean, you know, 10%, 15% of the wheels might have flats like that. That's what systems give you free of charge if you ride on them, particularly if you ride on the bogie rather than the centre of the car. People used to pay to get that kind of vibration being transferred up your spine. It used to cost about 20 cents or 50 cents if you stayed at the right hotel. Now you can get it free of charge if you ride on some of these systems. Noise. Very interesting. Noise, of course, if you get corrugations, the noise will come from your corrugations. The noise will come from all these kinds of surface irregularity, wheel burns, squats, wheel flats, and you also have, now he comes in. Sorry, I stand unprepared here because this is a unique system. You got it on max level. You also have this wonderful noise. This is very soothing. It's a lullaby. And people pay very big money buying apartments next to railways to listen to this noise. Here you can perceive two kinds of noises. Flanging noise. That's the wheel flange making contact on something. And here is the pure, beautiful tone of noise. Heaven. Okay. Railways are really getting stewed over this. You know, they're getting sued left, right, and centre, and they never, you know, all their complaints are associated. That's nice. Now, can anyone imagine a purer tone than that? You really have to go and listen to the orchestra, Melbourne Orchestra, whatever, to get something like that. It goes on. That is a coal train, by the way. Way of explanation. That is a coal train in the Hunter Valley, empty, going around a curve. Okay. You've become excited enough. Early days at BHP. Talking about a wonderful case study, the BHP one. And I'm only talking about the early days because people like me with Alzheimer's really have to think about the early days. They can't think about what happened yesterday. Today. Is it today? Everyone should appreciate operations of Mount Newman began in 69. 1969. And the track and vehicles were designed according to the highest US standards, you know, really great guns. So we had 132 pound rails, which in conversion is 66 kilogram per meter, standard carbon, 1 in 20 grade C conical wheels, hardwood sleepers, 550 millimeter spacings, well graded ballast, nice and hard, 3-piece bogies, heavy duty bearings, heavy duty couplers, heavy duty everything, and a very small proportion of tight curves. Well, you know, one can expect this. Most of it is desert, so you really have to have a straight track, and it's only across the Chichesters that you have a few curves. Minimum radius was 582, beautiful curves, and 3.9% with radii less than 900. Now, initially the track was designed for 8 million gross tons a year. Please keep that in mind, 8 million gross tons per year. That was achieved in the first 6 months, by the way, but I'll talk about that a little bit later. So that was the design. What happened in relation to the wheel rail problems? Okay, in 1971, that's 2 years after it started, it already had 30 million gross tons over the track. We started to get corrugations in the high rails of the curves. Unseen, you know, there were shallow curves, and these corrugations started to appear. By 73, 74, the annual tonnage, of course, had increased to over 40 million gross tons. This is business at its end degree. 75, the wheel set, we started to see very, very severe gauge face wear and wheel flange wear in straight track. Lo and behold. So, and it was cyclic. It went from one side to the other, to the other, to the other. So obviously something dynamic was occurring, and the problem of hunting started to be spoken about. Now by 75, there was sort of talk about shutting down operations for a little while because the trains were not running very fast in the straight track. And so on. So this sort of encouraged management to start thinking about what we should be doing in terms of long-term research. And there's nothing like a panic situation. In 77, the wheels had extremely limited lives, 300,000 kilometres for several cuts and so on. And so we said, okay, how can you reduce wear? Well, we introduced a profile that would give us a very good, very high rolling radius differential, the one that I had a great big cross at initially, and that made just 1 point. And of course, on the rail, on the high rail. And when we did that, the wear went down. The defects went up because we had exceeded the limit of the materials, and we had transverse defects coming out everywhere. In matter of fact, it was one of the first times. Jesus, sorry, I just had a relapse. What's that analysis that where you can plot anything against anything, and you get a beautiful straight line? Sorry, no. What is it? Weibull. Yes, sorry. Weibull analysis. I'm terribly sorry. Jesus, I was going to impress someone, and I cannot forget what it is. The Weibull analysis. You use the Weibull analysis, and you always get a straight line by plotting anything against anything. And that's where we use the Weibull analysis to show that we're in trouble, real trouble. So here we had a situation of the wear versus fatigue dilemma. 71, so the changes, what happened? 71, we said there was just general grinding to control the profiles in curved track and control the corrugations that were occurring. In the mid-70s, we actually changed the cant of the rails so that we tried to reduce the gauge corner defects. 77, 79, there was a major rail grinding effort, because what we had to do in tangent track, in the straight track, that had all this cyclic wear, is to change one rail for the other, and that's called transposition. It's generally not used very often, but when you're in a panic, you do anything to keep the trains going. So here we are. So obviously, you know, when you change the rails over, you change the profiles totally, and you've got to get back the profiles to some kind of thing or another. So there was major rail grinding there. In 78, 79, we started to introduce improved rail lubrication practice to reduce the wear and the wheel flange wear. In 78 plus, we started to introduce 68 kilogram head hardened, high strength head hardened rail, heat treated rails. And in 79, we started to introduce the same material type in the straight track. In 79, 80, we started to introduce asymmetric rail profiles. Ravi, I think, mentioned, or someone mentioned that. And we also reduced the wheel flange clearance. They were running very close, so that the wheel flanges were running very close to the rails. And that was the general procedure adopted by most systems. Indeed, it is the general procedure adopted by most systems today. So that's how much we have gained in the last 45 odd years. So people like running a tight gauge. I've got to go back to the original, to the outside. We had to push it up, push it out, and instead of 5 millimeters, we pushed it out to 9 millimeters gap. That's the gap between the wheel flange and the rail face on each side, 9 millimeters on each side. And that actually led to a reduction in wear by 25%. Bang! Overnight. We did that and the wear went down 25%. When you do that and you're in a research environment, it's fantastic, you know. People come around and saying, how much would you like next year? Money-wise, you know. Can you get another 10% out of it? Sure. In 84, we actually introduced the narrow flange and modified profile, which was based on a worn wheel profile shape. And essentially the kind of profiles that we're talking about are in the high rails of curves here. Here's the wheel, here's the rail. You can see nice conformal contact in the gauge corner, wheel throat. That's called conformal. In the low rail center of the rail, in the tangent rails, you have usually most of the wheels are here, but some of the wheels will migrate towards one rail, and you have a gap between the wheel throat and the rail gauge corner, and that's called 2-point. Okay. Some of the benefits, we relaxed wear limits from about 30% to about 50%. We reduced the rail wear rate markedly. We reduced the defects, the fatigue defects. Corrugations became a thing of the past with the preventative grinding and so on. So by this time, we increased the rail life 2 to 3 times. And as it was mentioned before, we started to get the gigaton rails coming into play, and I took great pride in actually publishing a paper many years ago. It was presented at Adelaide, saying how do you get the gigaton rail? Never before. The wheel life increased from 300,000 kilometres to over 2 million kilometres. Not bad. That's not bad. That's when they come around and saying, can you make it 3 million? How many $1 million would you like to have? Fuel consumption down by 10 to 15%. We killed off all the lubricators in the track because there was no need for use of lubricators. By doing that, of course, the traction went up because locomotives, so we didn't need as many locomotives to pull the trains up. And of course, during this time period, we went from 30-ton axle loads, then first of all to 32.5-ton axle loads, impossible, and then to 34 to 35-ton axle loads. And this really worried our Yankee colleagues because they didn't want to go higher in axle loads. And then of course we went further and further up, but I'm only talking about the first 20 years, so that's it. More to come in the next lecture that will be given by Peter Mutton or something like that. Right. So that was it. That was not a bad case study. The thing that I should emphasize with that case study is that conditions were with us because there was panic in the air. And when there is panic in the air, unlike love in the air, people cough up. And then people look towards the future and they don't say, oh, that's going to happen next week. Come back for the week after and we'll talk about your next budget and so on and so forth. Things went relatively smoothly. And I mentioned before, some of the reasons why that was so was that the guys that went over there knew stuff all about railways. So anything went, anything, they didn't even look at the standards. This one was very interesting. There was a wheel rail, there's a lot of work done in Australia, by the way, between the BHP and the other systems, of course. I've only got time to mention 2 case studies. The Wheel Rail Interface Committee that was set up in November 1997. The study was actually initiated in 1999, and the aim of this committee, of the outcome, primarily was to develop generic wheel and rail profiles that could be used through all the systems, all the interstate standard gauge systems. And we had, the committee consisted of all the main representatives, of course, State Rail, National Rail, Freight Corp, IRTC, etc., etc., etc. So it was a pretty good aim, improved wheel and rail life. The outcomes of the project, by 2001, the analysis, profile development and field testing had all been completed. And what came out of that was that we developed one wheel profile to suit all traffic. And that was based on a worn kind of wheel profile, which is similar to the kind of work that we had done for BHP. That profile was called WPR 2000. And then we developed 2 sets of profiles. One set mainly for passenger traffic, and one set for freight traffic, heavy-duty freight traffic, for curved track. So you had 2 sets for curved track, and 1 profile for tangent track. All straight track and shallow curves in Australia. 1 profile. Not bad. Worked like a charm. The difference between the old one and the new one, I will show here. This is the old one, ANZR profile. It's a conical profile with a 1 in 20 cone surface. This one, you can see it's got more beef in this area, and it's sort of a worn in inverted commas, and this beef is required there so that it can make contact in the gauge corner region of the rails and of the high rails in curved track and give you a high rolling radius differential. So that's it. That's in the new condition, of course. And a wheel profile is wonderful because you can machine. It costs nothing to implement except a set of tools, a template. That's all you need to introduce a new profile. To introduce the rail profiles, of course, remember you have to call Ben in Perth, and he will talk to you sometimes. I love the man. It's sort of okay. So this is what the profiles look like. This is for the passenger traffic, lower axle loads. You can see the contact. It was quite narrow because the applied loads were not high. In the low rails, it was relatively central. This is the high rails. With the higher axle load traffic, we increased this contact to reduce the stresses. The low rails was pretty much the same. And here is your contact on tangent rail, central. That's new. Now, when we looked at this, implementing this profile particularly in New South Wales were very keen on this profile. The other states were sort of a little bit out. And New South Wales had a big voice, which is fair enough. Someone's got to have a big voice. So we implemented those profiles in the Hunter Valley. Big voice. big bucks, and also in Sydney. And what we obtained was a reduction in wheel flange wear ranging from 25 to 40%. That's pretty good. And also, in terms of the rail wear, we reduced it by 20 to 30%, just by changing the wheel and rail profiles. So the Hunter Valley said, yes, lovely. Sydney said, yes, lovely. We also did some limited field trials on rails that had been modified, and we ran passenger trains up and down, and they proved to be very successful with no problem in stability. So up till now, it looks good. It looks really good. At that time, we sort of said, okay, fine, here it is, you have it. And we withdrew back to Melbourne, of course, the safety and the cocoon of Melbourne. As I said, you can implement a wheel profile very, very quickly. All you need to do is to take your wheel set up to the lathe, and the lathe will go zip, zip. You've got a new wheel set, new wheel profile. So everyone started to implement the new wheel profile because they were very keen. Unfortunately, the thousands and tens of thousands of kilometres of rail track that you have is a little bit, rail grinding takes a little bit longer. Like, it's not happens overnight, because you only have 2 or 3 grinders around the place to cover about 40,000 kilometres of track. So the rail profiles were not implemented for a number of years. Like they're not implemented now. Okay. So here is all these new wonderful wheel profiles running over unground rails. And unfortunately, what happened, of course, is that they started to play havoc. They started to hunt. The wheel sets started to go from side to side, simply because the assumption, stupid assumption by the researchers and the committee, that we would have modified wheels running on modified rails, and we didn't. So that was a bit of a question mark. I think, as I said, I think this is a good case study for things in the future. So we, 2007, that's when there were major reports of wheelset bogie vehicle hunting problems on passenger and interstate freight operations. And this sort of is a simplified, these shows lateral oscillations of wheel sets containing the new profile, WPR 2000. That's a WPR 2000 that has a narrow flange, and that's the original ANZR. So you can see that the ANZR is considerably more stable laterally than these two varieties. And once you start getting those oscillations, of course, that's a nasty thing, particularly if you're carrying eggs or something like that, or passengers. And once again, I keep on saying that, people, if you're travelling on something like that, and you get rocked from side to side, you should be happy, and you should actually be paying the railway as a first-class passenger. But I believe that those oscillations actually play havoc with your guts. This is not very good. Anyway. So another thing that actually happened that we didn't come to fruition in our minds at the time was that, as I said, the first trials that were done on ground rails, almost brand new rails in New South Wales. So they were pretty good. We forgot that actually rails all over the place have mushroomed with time, as I mentioned before. So they've got this lip here, this nice little lip here, you see, and that actually tightens up the gauge. It makes up two things. Tightens up, a number of things that make the gauge tighter. So the rails were not ground to the right profile, if at all. The track, people like ordering sleepers with tight gauge for some reason. Gives them a sense of confidence. I don't know why, because if you make it too tight, I don't think the wheels would actually run over that system. But there is a limit. So usually railways order their sleepers with a tight gauge But when they place the rails on the sleepers that have a tight gauge, and the rails actually have these bulges, which tighten the gauge even more, you've got no gauge left. Or you have very little gauge left. And of course, those conditions, if you have a worn kind of profile, the worn profile will ride on that point, which is a no-no point, because as I remember in my second, third slide or whatever it is, that's the point of very high effective connecity and very high rolling radius differential. Ba ba ba. It all makes sense, doesn't it? Okay. So that's a real problem. So consequently, these were the results that came out of the review that the freight and passenger traffic on interstate lines have actually gone back to the conical wheel profile now, and which has the greater, for stability reasons, but of course you use that profile and you have much more wear. So, but that's a track problem. That's fine. So the lessons to be learned really was that now the Wheel Rail Interface Committee needs to establish, or is establishing, new guidelines for future profile implementation, and there's a general opinion that you can't really just have a minimum number of profiles. You've got to have a number of profiles to suit conditions and so on and so forth. So that's something that will be is going on at the moment. Where are we now? We know a lot about surface defects, but not all. There's still a lot of some questions. Why these squat defects develop from those rolling contact fatigue defects that I mentioned. If you have 10 million of these little fine cracks on the rails, you may have 100 of those that actually grow beyond their confines. Why does that happen? Who knows? Well, maybe someone knows, but they haven't made it simpler. How fast do corrugations grow? And what drives them on to keep on growing? We know a lot, but not all, about rail wheel wear and lubrication. We've gone a heck of a long way. But there are curves that have differential wear from one end to the other, which doesn't make quite some sense. How do we, we have manufacturers that come to systems on a yearly basis or 6 monthly basis and say, I have the good oil for you, good lubricant. Trust me, it works in the winter time. 1 month. And the summertime. 1 month, as long as the temperature is between 25 and 26 degrees centigrade. We know a lot about rail grinding and profiling, but how can we prove the cost effectiveness of grinding? Grinding does cost money, and often it is misused in preference to other systems and so on. So the rail grinder, in a number of occasions, if you have a weekend to do all the maintenance, you only bring the rail grinder in for the last 2 hours, and every other frigging machine goes before it. And so people like Benny and Mick choose their, that's why I've got no teeth left, by the way. I've chewed them away. We have the wheel, now we have actually the tools to monitor wheel and rail profiles. Running around the system, you have a wheel profile, we can monitor at several locations around the countryside. Laser systems, light systems and so on. Very accurate measurements of wheels going by. And we have, I think, 3 of those wheel profile measuring systems. And rail profile systems, we have the AK car that is owned by Railcorp that goes around everywhere and measures rail profiles. Okay, sometimes it misses 30% of them, but that's all right. The thing about there's millions and millions of bits of data now coming out of these systems. What do you actually make? How do you use this data? We're getting swamped, really. Or some people are getting swamped. I don't really care anymore. I mean, who gives a stuff? But yeah, lots and lots of data, but what to do with it? We know a lot about the adverse influence of core wheel and rail contacts on the critical stresses. And hence, of course, headwear limits. How far can we push, how far can we wear the rail out? And therefore, what is the wear life of the rails? One of the odd things is that you may think about a rail section. It's sort of a bastardized I-beam structurally. It's a real bad I-beam actually, because it has a foot, it has a very thin web, and it has a big head. Now, I-beams, of course, structurally are wonderful if you only apply vertical loads to them. If you start to apply eccentric loads, I-beams don't work out too well. And of course, this is the situation when you have a rail and you have a wheel, many wheels that sit over this side of here, you get a rail rotation occurring and a rail moment, a rotational moment being introduced into the rail section. And of course, your stresses go high, and of course, you can't take, your wear limits go down, and so on and so forth. Very limited work has been done to actually change the rail section. The best rail section, by the way, now we have tall rails, very tall rails, with a big head. It's getting bigger, because the Americans like them bigger, We produce our rails big. With a big head. The concept about why do you need a big head? Because you're just going to wear it out very quickly, doesn't really goes into the North American mind. Very little work has actually been done with a redesign of the rail section. And as I said, the best rail section is actually a very squatty rail, one that has a little baby foot, a big web, and a big head. You used to, I've got a name for them, they're called crane rails, and they were manufactured probably 40 years ago, 50, 60 years ago, and they were put under cranes. Fantastic design. I mean, that's the best design. They had a big fat web, it was almost like a square, a little square, or cube, of course. So anyway, nothing much has been done in that area, unfortunately. Well, I don't know why. We have very, very sophisticated dynamic models that to some extent can simulate how a vehicle wheel set bogie can go down the track that has one or more defects and so on. And there are three major models. New cars from the US, and that's mainly for vehicle-track interaction. You have Vampire from the United Kingdom, and again that's vehicle-track interaction. And then you have this third model that has been brought over by IRT from Russia, universal mechanism that actually has, you can look at both wheel, rail and vehicle track. And that can be used to examine a wide range of things. And just as an indicator, this shows the lateral displacement of a wheel set for three wheel profiles with different conicities at a particular speed. And you can see that the profile that has a lower conicity, this one here, the oscillations dampen out, that's the blue line, will dampen out very quickly. You've got your track defect here, whereas if you have the 0.15 effective conicity profile, you can see that the oscillations keep on going. Now, if you introduce another defect here, of course, the oscillations will keep on going, so on and so forth. Now, so these are very good models, but the models really are not often applied. It's not a common thing to say, yes, let's go to and let's study this particular aspect through modeling.